Okay, could somebody mind putting something in the chat so I can see if I can see the chat? More chat. Okay, great. Thanks, AJ. Cool. And I think I recognize a few of you. Hey, Maki. Hey, Mihir. So yeah, thanks for having me. I'm excited to hop in and talk about our work a little bit. So my name's Hayk, and I lead the autonomy team here at Skydio. And I'm going to talk about robust visual navigation and real-time 3D reconstruction on board Skydio drones. So I'm going to talk a little bit about why we do what we do, and then kind of split into two halves. The first half is this kind of just how do we get our drone to navigate autonomously, avoid obstacles, do the things it does to basically be an intelligent flying camera. And then the second half, I'm going to talk about our new work in real-time 3D reconstruction and 3D scanning, which has just been our biggest focus this year. And so again, this is, to get you guys hopefully interested, provide some insight into robotics happening in the industry. I'd love it if people just ask questions anytime, anywhere. I have probably more content than I can go into, so I might be jumping around a little bit with the visuals. So if you just drop things in chat or even unmute and ask, I'll get to them right away. So, all right, let's get started. Okay, so Skydio, I've been here for about 6 years. It was founded in 2014, and we're now, this should be more like 200 people. And we basically are now the largest US drone manufacturer and considered a world leader in autonomous flight. So we're headquartered in Redwood City, and we do everything here, and we've raised about 170 million. And we have a fantastic just set of people across our team. And it's cool to be at a company that sees all the different functions, not just the robotics software, but everything being integrated together to make that happen. And as we'll see, that's a really important part of making it really work. So our mission is to make the world more productive, creative, and safe with autonomous flight. And I would say we have three kind of major focus areas. So the first one, which has been the focus for basically our entire lifespan until this year, is cinematography. So capturing amazing moments with an autonomous drone. That means you're basically not the pilot, you're the person doing the skimboarding here, and the drone is taking care of the rest. And I think we've seen a lot of success at that. And now we're also focusing on broader commercial applications, so inspection and mapping. And this is the one I'm most excited about, which is just all critical infrastructure in the world. If you think about all transmission towers and cell towers and bridges and buildings and house rooftops and highways and railroads, like all this stuff is built. It's very expensive. It's old. It needs to last a long time. So it needs to be inspected, monitored, and it's an enormous industry doing that. And often it can be very dangerous, very expensive. And so it's just a huge amount of value add that drones can have. And also situational awareness. So if you think about fire, police, active shooters, kind of a SWAT team or a soldier looking over a hill, like there's just a huge value to having a camera that can do this for you and can save lives. So those are the main focuses I see us having. And I think most people are familiar, hopefully, with the Skydio 2, which is the mainline drone that we launched just over a year ago, which has these 360-degree vision and obstacle avoidance. So through these 6 navigation cameras, and I'll talk about them in a little more detail, but they're really cool because each one is 200-degree field of view and fisheye. And so we have this trinocular setup on the top and the bottom, and that allows us to kind of fly in any direction and avoid obstacles and see things. So I just want to show maybe the first minute of this sounds worth it, which is kind of like our customer highlights from this year. I wouldn't have even thought of Skydio 2. Absolutely insane. I can't even believe this thing, man. This is a game changer. Insanely dynamic shots that are effortless. This thing is crazy. It's just avoids all these obstacles like nothing. Our personal helicopter pilot is here. This thing will give you the most amazing
amazing shots.
Okay, I'll pause it there in the interest of time, but it's exciting. It's exciting to see that we made a robot that a lot of customers buy and love, and it works out in the world. So, like the fun quotes here about the product that motivates us. And again, this is really showing that we've kind of hit the, autonomous cinematography use case well. And then, so we're now gearing up for the release of our Skydio X2 platform, which is a larger, kind of more rugged, more secure platform for enterprise commercial use cases. And the core electronics and the software is very largely the same, but it has longer range, longer flight time, has a thermal camera, so all these things that become important. And I'm not going to go much into this. I think we've covered it enough, but there's a huge, enormous amount of need for robust, reliable, safe, intelligent, trustworthy drones to accomplish tasks. And some of the examples you can see here is just the cost of police helicopters, the cost of climbing towers, and the human cost of injuries and death. And things like bridge inspections are just horribly complex. Like, look at these trucks. I think I have a picture of an accident with these trucks. Utility inspection is incredibly, like, people actually touch a rod to this power line to and then it arcs and grounds the people. Then they shuffle on and basically clip themselves into the power line and crawl along the line inspecting it, which is just nuts, if you ask me. And yeah, so there's just a huge amount of cost savings and interest in tackling these applications with drones. But a lot of drones can't fly under bridges because there's no GPS and it can be dark, you can be over water. It's a very tough visual environment. So that's kind of what I want to focus on. But I hope I've driven the point home that manually flown drones solve some problems, but not most of the problems. And it's a big issue scaling up to all the use cases that there's potential for. And we think autonomy is basically the key to accomplishing that. And the more we can do in software, the more value add we can provide, the more applications we can provide with the same kind of drone, with the consumer grade hardware, and the better everything works out. So we really think about it as software driven devices that can move around in the world. So we have this kind of architecture that thinks about the whole stack up from the hardware and the controller to the core autonomy that makes it work, and then these high level applications, the most exciting of which is 3D scan, which I'll talk about. So, but first talking about the core. So this is kind of like an old diagram now that shows kind of a traditional perception and planning stack that you might see in a self-driving car system. And it's all these components are, interesting pieces of computer vision research that we've productized and fit into our system. But the thing that's most important is that they're very closely vertically integrated and work together efficiently. So I'm gonna go in detail on some of these topics, and I just want to open up with a video here that shows some of what the drone is seeing. So here's an example of following a mountain biker, and you can see we're in lead mode here, which means we're in front of the person. So that's a lot harder because we can't just follow in their footsteps. And then when we hit a couple of kind of a narrow tree gap, we flip around and then we go back, and you can see the drone is doing a pretty good job of maintaining cinematic video while avoiding these obstacles. And then of course, the interesting thing on the right is that we're looking at kind of a stitched full 360 image from its navigation cameras. So the The fact that we can see all of the context is pretty key to being able to fly backwards while looking forwards. And the bottom right here is a depth map. That's the result of the autonomy system um, that shows what's being seen by the drone. Okay, so yeah, so this slide shows a lot of difficult visual conditions from our cameras. And this is, I think this is basically almost the best summary of what makes the core navigation system really difficult to make work in the real world in difficult environments. So I'll talk about a few of these. So I think the classics are like thin branches are just hard to see. They're thin, they can get over or underexposed, especially when they're very close to the camera. As humans, it's incredibly hard to pick them out, especially without motion when you're in kind of a dense forest environment. You can see them when they're against the blue sky here quite easily. But we've so looking at and similar to thin branches are wires, and we'll look at a little more about the obstacle avoidance performance on those. So moving waves, reflective water, low kind of flying over water. It's very tricky because water moves, it's reflective, it's treacherous. You really can't touch it at all. And then, so textureless wall conditions, low light, snow, dirt, smudges on the lenses, reflective glass. There's many difficult conditions for visual state estimation and obstacle avoidance. And this is what we've spent years working on. And some of the things that make that hard is that, so with a drone, there aren't a lot of semantic priors. So it's pretty different than driving on a road and expecting a certain set of kind of pedestrians and cars and street signs. And those things all, there's tons of edge cases there too, but with a drone, you can really be in the middle of anywhere and you can't really rely on what your some kind of base semantic case, like there's a ground plane, there's buildings, and then there's this and that. And there's, you're flying robots. There's not a lot of room for error. So you can't miss something or else you might crash into it. You can't imagine something or else you'll make erratic, unpredictable motions. And you can't just stay where you're hovering a lot of the time because then, somebody might get away from you. So all the error handling there is extremely critical, and the ability to kind of degrade gracefully and handle as much of this as possible. And I'll talk about several instances of these things and how we kind of handle them. So the core of that system that kind of does the handling is our state estimation system, since that's the most base sort of visual system that everything else relies on. So we have these 6 navigation cameras, and we have to estimate how our robot's moving. But that's not all. We also estimate IMU biases. We estimate the camera poses. We also estimate the camera intrinsics. And I'll talk about why we do that online. And the interesting thing is these cameras are also rolling shutter. So why are they rolling shutter? Because rolling shutter sensors are much cheaper and lighter and higher quality. So just hardware wise, we made a bet that we could solve for the rolling shutter in software and gain the advantages from a cost and weight and size perspective. So our visual inertial odometry system solves for all these things jointly while we're flying. And that lets it work in really tough scenarios, like where you're just up in a metal tube and there's no GPS, and there's no magnetometer that's going to work in that condition either. And so that opens up a lot of those use cases, especially when you're flying around power lines and under bridges and things like that. So the rolling shutter, hopefully, I think most people probably know what rolling shutter is, so I won't go into it too much, but this is something that's, it's eminently modelable. And so the right thing to do is to model it, but you have to have very careful kind of treatment of it, especially time synchronization. across your cameras and IMUs. And then the thing that's pretty interesting is that rolling shutter, usually people only correct the rotation, but when you're a drone that's flying close to things and fast, there's significant translation effects. So that means that you're going to get a warping of things that's proportional to the depth of the thing. So if you're trying to solve for the depth of an object, you have to, it's kind of a chicken and egg with solving the rolling shutter. So you have to do it jointly. That's kind of the only way to go about it. Okay, and again, feel free to ask any questions in the chat. So this is a picture showing why we solve for lens camera intrinsics while we fly. So this is a thermal chamber with the temperature, and the arrow shows the kind of camera actually shifting its distortion with the temperature. And so if you're going, indoor to outdoor on a winter day, or your drone is in a hot car and then takes off outside, like these things will happen and change. So it's actually important to estimate these properties online. Okay, so moving objects, I think this is, especially water, is a really difficult problem. One thing that's pretty interesting in this domain is that when you're over water, usually, not always, because you've got the under bridge case, you hope that you have good GPS, and so you can actually trade off. And it's not simple to do so, to trade off between vision and GPS. It requires, it's a fusion problem where the two have pretty different noise characteristics, and understanding when to trust GPS can be very tricky, and also vision. So one thing that's pretty interesting that we've worked on is being able to use semantic information to understand what's water, what's sky, what's around us, to better inform our state estimation system. And this helps a lot. Because when you see these kind of waves, let's say you're following a wakeboarder, there's no other close features except than ones that are moving, and also not moving as a rigid body. So it's quite challenging to deal with if you don't know not to trust those, and you're relying on kind of outlier checks, because everything's kind of an outlier, and that's not good for outlier checking. Is rolling shutter correction done as part of joint optimization, or something like that done iteratively but separately from the rest of the estimation pipeline? So the short answer is that rolling shutter correction is done joint. Rolling shutter is accounted for in all of the estimation and obstacle avoidance systems that we have, because it's important to do so. And I think that's basically important to do. So the rolling shutter model itself doesn't necessarily need online calibration. It's a model, but that effect where you have rolling shutter translation depends on the depth of the scene, means you do have to solve it jointly. So good question. Okay, so obstacle avoidance. So this is probably the system that I'm most proud of. So we have this full 360 obstacle avoidance, and we did years of research to kind of get it to the point where it's at today. And so it's noted here. So I think I have a slide on this, so I might just skip forward. Yeah. Okay. So basically, we use deep learning for our obstacle avoidance system, and this is something that's very new. So in fact, we were the first team to actually demonstrate complex obstacle avoidance using deep learning. And I'll talk about this paper that we first published, and then the progression into that. But it's a very challenging problem to do, because first of all, there's no ground truth for the real data. So we have billions of images recorded from our internal flights. So it seems promising to use unsupervised learning, and there's a lot of those techniques that have been explored in the past several years. However, the problem is that for any difficult cases, photometric consistency can fail. And this is, if you think about thin objects where a different background can dominate the photometric signal, or a textureless surface where you have reflections, or a thin branch that just doesn't have a lot of, presence in a cluttered background. The photometric signal is not there. And so what you get when you learn just in unsupervised ways on real data is that you tend to learn the easy stuff, but not the hard stuff. And that's obviously a problem. And so we've worked a lot around how do we balance that in different ways to actually learn from real hard examples to improve. And I think we've done that. But it took kind of years of engineering effort. And I think that's one of kind of my meta, I don't know, principles, is even for kind of researchy computer vision tasks, the engineering is usually more important than the kind of underlying research. So the first paper that we published on this, I guess the only paper we published on this was called End-to-End Learning of Geometry and Context for Deep Stereo Regression. So this was in 2017, and we were kind of the first to not just learn the depth, but incorporate learning into a kind of something that looked like a traditional stereo pipeline, where we had kind of a tower that extracted features from each of two images and then combined the features in a cost volume like thing, and then did a regularization of that volume. And it actually worked quite well. So in the middle, here's our prediction on Kitty. And we got first and second place on the two Kitty benchmarks, but it was quite slow. So as I mentioned, in about a year and change from there, we were able to run that for the first time on the drone and demonstrate it flying. And it was about 1,000 times faster than that. And this used to be a video, but it's not a very exciting video of an ATV driving around. And then this GIF is just an example of something that we crashed into before that our non-deep learning system couldn't see, but that our deep learning system does see. And I really like the value of deep learning is really present there, because you can just see cases where we had no way to kind of think about how do we code seeing thin branches better, but now we can collect data, we can enforce loss, and there's just a lot we can do. So it's almost like going from feeling powerless to having the ability to influence in complex ways what the system is doing. So here's some thin branches. Yeah, sorry, power lines. And I think we've gotten to the point where if you can mostly see it in the image as a human, you will pick up the signal. But it's unfortunately the case that often these, the thin power line signals might disappear into the image as well. And then finally, I'll show some of this is flying around in our office. So here's a point cloud. Okay, I see a question. So could you comment on your camera IMU synchronization? So sure. So basically we synchronize our cameras in IMU we in hardware, and then we also basically track, there's a lot of layers in between. So we time synchronize kind of a fixed offset between them, but they are triggered in hardware roughly together. So that's pretty important for making things work as tightly as they do. And then, are you using hardware accelerators for your onboard deep learning algorithms? So on the Skydio 2, we just have an NVIDIA X2 or a Tegra processor. So it all happens on the GPU there. Okay. In the interest of time, I'm not going to talk about this in detail, but basically we actually have a system to detect when the cameras are smudged or have a crack in them, and we actually will mask out regions of that. And then if it's bad enough, basically highlight to the user, oh, looks like your camera's smudged, you should land and wipe your lenses. So things like that are super important for actually making a robotics product. Here's a pretty cool little feature. So the ability to kind of pull out from the main user camera view into a 360 contextual view and then into a digital zoom of the view lets us have this kind of 100x zoom range that's pretty compelling for a pilot navigating in different scenarios. And then, of course, we like to talk about how close in we can get to things, and always like to ride that line. Okay, so our planning and control system is also pretty incredible system. So we jointly will solve a unified optimization problem that thinks about the entire vehicle state, the rotor rates, aerodynamic effects, obstacles in the world, cinematic constraints, and all sorts of high level objectives. And we do this at 500 iterations a second, and that really helps basically be able to push the hardware to its limits and not have unexpected kind of saturations you might have from a traditional quad rotor control stack. So if you're familiar with kind of the differentially flat quad rotor model and cascaded controllers, that's what we had on our first drone. And there is kind of a world of difference when you're able to actually model everything together rather than assuming a cascaded series of dynamics that are independent, because they're really not independent. And it's worth highlighting our skills API. So we have this Python layer that allows people to write code to run the drone in a way that doesn't cause the drone to crash and is basically safe. So it's kind of like a sandboxed application layer for our drones. And actually, if you were to join Skydio, the thing you do on your first day is basically write a cool, fun skill to control the drone and actually be able to push that on a drone and fly it on day one. I'll show this just because it's really cool. So this is from a while back, but this is showing 4 drones following and filming the same person here. As he goes down a water slide. I think one of the drones picks up the wrong person here, but 3 of them get to go down. Okay. And then just to highlight that we put a lot of work into our systems infrastructure. But besides the sort of high performance compute environment on board the drone, where every metric counts, memory usage and CPU usage and GPU usage, and it's just highly optimized to work well together. We also focus a lot on log data and simulation data and how we can basically pull out regression suites from those to get statistical results and not just kind of make one thing better and one thing worse, but actually have a large repertoire of systems that we can say that we're improving upon. Okay, and then skipping forward, so leave some time for 3D scan, which has been, I think, the most exciting thing we've been working on this year. There's a question: if I understand correctly, you rely on deep learning for even depth estimation. What are the operations you still rely on classical approaches for in the perception stack? So it's a good question. And I think one thing I'd say is we like to blend like we like to blend 3D geometry, some classical approaches, and deep learning. So it's not necessarily that everything is just one big deep learning block, but it's blending what is good for learning with what isn't. But I will say largely that at least the planning and control system and the kind of core of the state estimation system are kind of large optimizations rather than deep learning approaches. Okay, so 3D scan, the idea here is, we have a drone that flies autonomously, avoids obstacles. And a lot of what people want to do with drones is take images of things and build 3D models. And expert pilots can do this um, pretty well, but it takes a lot of training. And people also use laser scanners and they fly with Cessnas. But what we realized is we're kind of in a perfect place to do this, where essentially the drone can, the operator will select, and this is just showing all the different classes of things that would benefit from inspection and mapping and 3D modeling. Um, so the basic idea is essentially that you pick a 3D volume with the drone, whatever it is, and the drone will just do the rest. So it'll go in and it will build a real-time 3D model of what you're looking at, and it will make sure it captures every surface to some desired overlap and resolution so that you can build a really high quality 3D model offline. So basically, in order to know what data to capture online, we build a low poly model while the drone is flying, while we explore the structure like you see here, so that offline you can build a really high quality model and do inspections. And so there's a whole suite of kind of new algorithms on top of the core navigation stack that we've built to do this. And it kind of comes down to that it's not just a locally consistent state estimate and map for obstacle avoidance, but it's a globally consistent map for doing structure from motion. So the thing that's going when you are running 3D scan on one of our drones is that even across multiple flights, there's no trajectory drift. We're matching back to basically the very first images that we took and aligning everything in a large pose graph. So basically doing real-time structure from motion. And then we take that and we plan a path. So we dynamically kind of come up with what is a strategy for capturing the model as we know it. And we kind of iterate on those two things as they both improve together. So this will show a little bit of a video of that, as we're starting to connect these poses together and improve the map that we see below. And then this is showing some examples of how to think about the dynamic scan planning. So there's a lot of different algorithms you can think about using to say, how do I capture everything at the right angle, at the right resolution? And a lot of it comes down to what it takes to do photogrammetry. So how many images do you need of each point? What causes failures or gaps? So this is showing a kind of a cool thing that we can do, because we control the whole system, is be able to visualize kind of in AR what the drone is thinking, what it's covered and what it hasn't as it's flying. So that's an example of that on this windmill here. And then on the right is showing kind of this, what we call a coverage mesh, where we've colored the mesh by where we got good data versus bad. And this is something that we can show in real time or after a flight to kind of understand how well we did, or even if you flew manually, how well that happened. And a neat thing here we've come up with is actually the drone can serve a web server. So you can kind of log in without any internet, just onto the drone and explore around this structure, look at the images, and even do your inspection. But at least make sure that if you're an operator that drove out hours to some remote site to inspect it, or you're a cop and there's a highway accident, you've closed down the highway and you're never going to get back this scene, that you've captured the right data that you need. And then I think I'll basically finish with this example, which is something that actually I captured in just 2 flights. So in under 30 minutes, the drone flew around, autonomously captured this bridge, and then I reconstructed it in a photogrammetry package in about 20 minutes. And so it's pretty exciting what is possible to do there. Yeah, and then I'll just highlight, we have this vision of when you add docking stations, you add cloud connectivity, that there's no longer a one-to-one pilot relationship. And you can have these worldwide fleets of drones that act as a service. And we like to call this like Skydio Earth. So if you think about Google Earth, but you can build maps at 100 times or 1,000 times the resolution, and it can be a live view at the click of a button because you've got a drone and a dock. And if you're an energy company like PG&E that has hundreds of thousands of transmission towers and something goes down, like that's a massively useful thing. So this is a little bit of how we think about the longer term vision. So yeah, that's a lot of what I want to talk about. And obviously we're hiring and excited to hear from you guys. So if you do want to contact me, my email is just hayk@skydio.com. And thanks for your time. So I see there's one more question, and then maybe you can open it up for all other kind of questions. Where did it go? So going back to the previous question, what applications do you think will be enabled by ubiquitous embedded hardware AI accelerators in autonomous quadcopters that are currently limited by computational capabilities? Well, I think there's tons of stuff. So for example, there are many things that we're limited in compute by. So one of them that I would love to do is handle moving objects better. So if you know the topic of something more like scene flow, where you estimate kind of all in 360, all objects that you see, their motions, whether they're rigid bodies, the ability to fly at faster speeds often comes down to response time. It also comes down to the hardware and dynamic response of the motors. But what you can see in how much detail is also a computational constraint. I think the ability to basically, like, anywhere the drone flew, build an accurate 3D map of, even if it's not a mapping mission, but because we have all the 360 cameras, can enable a lot of incredible stuff there. And there's also just tons of higher level applications of the drone is kind of a hardware device. And on top of that, you can run your own algorithm for some commercial use and actually load that onto our drone, fly it, be able to process that thing, and then run that essentially as a service. So that's some of what gets me excited about if we just had a lot more computation on board the drone. Okay. Any other questions?
Hi, this is Mark Badger. How are you? Thanks for this great talk. I had a question about sort of like the overall logistics of developing new research, keeping up to date on kind of current research, and the kind of how decisions get made, and like what are the different kind of personnel like roles for kind of deciding when to try and spend time doing something like just developing something completely novel versus like borrowing from existing research versus like we need to have this in the drone right now.
Yeah, that's a great question. A complex one too. So I mean, we're still pretty small. So as mentioned here, we're around just over 20 people. So we definitely operate in a kind of a collaborative way of just let's figure out what our needs are and what's the right place to focus. Very much encourage everyone to, we have paper lunches, we post papers, we try to understand the state of the art in both industry and academia. And one of the kind of principles we have is to be informed by the state of the art literature, but not be a slave to it. And what that means is that we may have different requirements than what that person writing that paper is going for, say, for that benchmark, or maybe it makes sense for us to have a simpler system in some area or a more complex system. So in general, I like to just be informed by what's out there, but do what makes sense beyond that to what we need. And most of, we do a lot of things that I think are considered research and open-ended stuff, but a lot of it, all of it is motivated by things that our product could do better and needs that we have, and kind of balancing where to focus our efforts. And in a world where we're growing and it's exciting and a lot of stuff is happening, we're in a position where there's a lot more stuff to do than we have the bandwidth to do. And so we just have to kind of, as a team, pick and choose what makes sense, and not be afraid of taking kind of the big, hard, risky bets, but being very careful when you want to do those things, and when you want to just focus on good engineering and maintaining the systems that we have.
Oh, that's really awesome. Thanks so much.
Yeah. Okay, so there's a question about, can you comment on sensor frequencies? What frame rate do you run your cameras, IMU? How do you tune those numbers? So I'm not going to give any specifics, unfortunately, on that stuff, but I will say that it's a lot to think about. So you can, especially your cameras, there's compute trade-offs there. There's all kinds of trade-offs. So if you think about, you've got all these different cameras. Which cameras do you process? What direction do you process? All of them or part of them? What frame rate do you process? Do you alternate between them? Do you run a more expensive algorithm on a smaller number or a cheap one on more? So allocating your compute budget in the most efficient way is something that is important, that we think about a lot. And per the previous question, if we didn't have to think about it, that would save a lot of time. But it's important to think about. And then another question is, why was cascaded control disadvantageous for the control applications? So that's a good question. And at the heart of it, so imagine that you have a motion planner that decides on your future trajectory on some horizon. That motion planner assumes that, you could go even simpler and say it's just a double, accelerator or something, or a double integrator, but let's say it's a differentially flat system. So it assumes you can go in any position and yaw, and assumes roll and pitch will do whatever is needed to accomplish that. Well, then you have a position controller that takes a track point from that and tries to match that. Then you have an attitude controller that tries to match that. Then you have a motor controller. And it's somewhere in that line, you have to handle what happens if your motor saturates and you can't have feedback anymore. And you have to come up with limits. So what people do is each layer of that stack comes up with kind of safe limits. It's like, my position controller won't command more than 30 degrees bank angle. My attitude controller won't command more than X kind of angular acceleration or velocity. And those are assumptions that will just break down. So in the planner, typically what people say is, if you can't meet the trajectory, just slow it down. Well, what if we don't want to slow it down? What if we want to fly the drone really aggressively because we're chasing an aggressive skier dodging trees? And so there's no unified way to reason about the limits that you're going to hit. And if that planner doesn't know about the limit of your propellers, like what's your max rotor rate, and that corresponds to very different kind of actual limits, because it corresponds to an acceleration limit. In some cases, it corresponds to a velocity limit, if you're dominated by aero drag and things like that. So the more it's just like you have different layers that don't know the full picture, the more you're going to be limited. So that's hopefully gives a little bit of an idea of why it's disadvantageous. Okay, well, it sounds like that's the talk. Thanks for listening in, everyone. I appreciate you coming in, and big fan of UPenn. So enjoy the rest of the semester.
Excellent. Thank you so much for your time today and the presentation. It was wonderful. All right,
Thanks,
Graspers, check
Charity.
out the next one on January 25th. I'll see you guys all then.
Thanks. Bye.
Thank you again.